Welcome to this third presentation. It's entitled The Bigger You Are, the Harder You Fall. There's a great meme that you see right here. It says, Newton needs new math to prove his laws, invents it. So we have a famous quote by President Barack Obama. It says, we need to steer clear of this poverty of ambition where people want to drive fancy cars and wear nice clothes and live in nice apartments, but don't want to work hard to accomplish these things. Everyone should try to reach their full potential. So the learning goals for this presentation are relatively short. We want to be able to identify the factors that affect gravitational potential energy. We want to relate work and gravitational potential energy. And we want to use the formula potential energy is equal to mass times gravity times height. So here's what we already know. We already know that work can be done lifting an object against gravity. So we can say, all right, if I take this object and I lift it up, it's going to require some sort of force to lift it, and I'm going to move it some sort of distance. So energy always has to be conserved. So in order for this work, lifting it up against gravity, there's got to be some sort of change of energy somewhere. And you may be thinking, well, yeah, there's kinetic energy as you lift it up, and that's true. But what about when you bring it to a stop up here above the ground? It no longer has kinetic energy, so what does it have? What we learned in the lab, the more mass an object has, the greater the energy is stored. So if you were to look at it, you say, okay, if we had one book, it has a certain sort of energy. If you have two books, it's got more. If you've got three books, it has more. So the more mass an object has, the greater amount of stored energy it has. Now you should be able to say, yeah, the greater amount of stored energy it has because the more work it takes to lift it up. We also know that the greater the height, the more work it takes to lift it up, the greater the amount of stored energy. So, potential energy. Remember, potential energy is where you can store the energy in some sort. It means the energy isn't actually moving. It's not actually being used at that particular moment. So objects above the surface of the Earth store potential in the gravitational field. And you see these gravity, it's just a theory. There's a lot of them where people are trying to test jumping off of cliffs to see if gravity is just a theory. Well, gravity is just a theory, but we want to make sure that we obey that theory or that law. So, the work equation. Remember, the work equation is W equals Fd. Well, if you look at W equals Fd, you're applying a force, you're lifting this object up against gravity. So at the very minimum, this force required is equal to the mass times some sort of acceleration. Well, if I'm lifting it up against gravity, a lot of times instead of saying A, we refer to the acceleration due to gravity as G. So another way of saying this is you can say work is equal to mgd, the mass times the gravity times the distance that you're lifting it up. So this is another expression that would apply to work. Well, we take a little bit different form and we just say mass times gravity times height when we're talking about potential energy. Whereas the equation that we did before was work is equal to mass times gravity times distance. That's how much I lifted it up over the ground. The amount of energy that's stored, though, is just the same thing. It's mass times gravity, which is the same thing, except we use the term h instead of d to indicate the height above the surface. Now the height and the distance are actually the same thing. Some books actually use these interchangeably. They are the same thing. So you see here, you see PEG. A lot of times people refer to it as potential energy, and then the little g means it's gravitational. Some books will use GPE, which stands for gravitational potential energy. So you'll see me use them interchangeably in examples, but know that they're the same thing. Since potential energy due to gravity is an energy, it's due to joules, and it must be calculated. Everything else we have lots of experience with, mass, gravity, and height. So let's look at an example. It says, what is the gravitational potential energy of a 5 kilogram book held 10 meters above the surface of the Earth? So above the Earth lets me know that gravity is equal to 9.8 meters per second squared. If it doesn't say Earth, you can just say that it's Earth, or you can imply that it's Earth unless it says something specifically to the contrary. So now we know that the height is 10. We know that the mass is 5, and we know we're trying to solve for the PEG. The formula we have is PEG is equal to mgh, or mass times gravity times height, is equal to 5 times 9.8 times 10. When you multiply all those things out, you get a PEG of 490 joules. In the next example, it says, what height should a 50 kilogram box be raised above the surface of the Earth to give it 2,500 joules of potential? So once again, we know Earth. This time I'm trying to solve for H. H equals question mark. The mass is equal to 50 kilograms. The energy that I have, I'm going to use GPE this time, is equal to 2,500 joules. And then I know I'm trying to solve for this. I know the gravity is 9.8 meters per second squared. The equation that I have is GPE is equal to mgh, or 2,500 is equal to 50 times 9.8 times, the height, which is what we're looking for. At this point, you can multiply these two numbers together if you would wish, and you get something along the order of 490 something. I'm going to instead just take both sides and divide it by 50 and 9.8. When you do that, it's going to cross out over here, and you have 50 and 9.8 on the bottom. Now you want to make sure that you do this in parentheses to make sure that you get the right answer. And when you do this, you end up getting a height of about 5.1 meters. The last example we have, it says, an object has 200 joules of potential energy when suspended 8 meters above the surface of Earth. The same object is suspended 5 meters above the surface of an alien planet. It has 5,000 joules of potential. What is the gravity on the alien planet? So there's a lot of stuff going on here. I'm going to start off with an Earth, and then I'm going to start off with, we'll call it planet X. Now on Earth, I know that the GPE is 200. On planet X, I know the GPE is 5,000. Now on Earth, I know that the height is 8 meters. On the alien planet, I know the height is 5 meters. On the Earth, I know gravity is 9.8. I cannot make that assumption on planet X. I can't do that. In fact, that's what I'm trying to solve for. Okay, so now what I need to do is I need to look at my information that I have. Now we do know this is the same object. So since it's the same object, it's going to have the same mass on Earth as it has on planet X. So if I can solve for the mass on Earth, that's going to be the same mass that I can then use on planet X to solve for the gravity. So I'm going to say GPE is equal to mgh. And I'm going to say 200 is equal to mass times 9.8 times 8. When you take these numbers and you multiply them out, you could turn and solve for the mass as being 2.55 kilograms. That now becomes the mass over here for planet X, because objects don't lose mass whenever they change from one location to another. They only change gravitational forces or weights. So now I have all the information that I need to solve for the gravity on planet X. Mass times gravity times height. I know that it's 5,000 joules of potential for this 2.55 kilogram object whenever it's suspended 5 meters above the surface of the Earth. When you divide both sides by 5 times 2.55, 5 times 2.55, you end up with a gravity of a very large number, 392 meters per second squared. That right there is roughly 40 times Earth's gravity and would squash you like a bug.